Now we're recording. Okay, thanks for the reminder.
Yes, we do need that.
Okay, let's start again. Okay, this is our virtual technical meeting of the IMAPS New England chapter. Um, a little introduction. The International Microelectronics Assembly and Packaging Society. We have regional chapters and country organizations. The New England chapter is the largest chapter in IMAPS North America, and the New England Technical Symposium that's run by our chapter is the largest and longest running IMAPS North America Regional Conference. This is the 47th year. It's a little different this time around because we've been doing it virtually, and it's been broken up into a series of sessions on a monthly basis, or roughly monthly. Um, the uh, the symposium is typically held in normal times on a Tuesday in May, and we have around 38 technical speakers, 55 exhibitors. All facets of semiconductor and electronics packaging, materials, components, and processes fall within our area of interest. So these are some of the recent events that we've done. Virtual chapter technical meeting. We've been doing those since the lockdown occurred back in April of last year. They've been actually very popular, and we're talking about continuing in future times with some combination of virtual and live meetings because they both have their advantages. And you can see sessions of the virtual symposium here, as I described. There was one in November, there was one in February, and I will be announcing an upcoming session after our speaker. Um, our speaker for today is Anastasia Patterson. She is a research investigator at DuPont in Marlboro in the electronics and industrial business. She's a technical lead in the Emerging Technologies Group, currently working on projects for managing materials refractive index. Before joining DuPont in 2019, she received her PhD in materials at UC Santa Barbara. And finally, and most important, she likes social dance and is looking forward to getting back onto the salsa or swing dance floor when things get a little safer. So take it away, Anastasia.
Excellent.
All right, thank you so much, Richard. Let me share my screen. And I will grab the chat and participants window so I can see if anyone puts questions there.
Oh, if I might bust in for just 1 second.
Please do.
Yeah, these are just standard reminders. I would ask that everybody stay muted unless you're the speaker or unless you're asking a question at the end of the talk. At the end of the talk, we'll have time for questions, and there are a couple of different ways you can do that. There is a little hand raise button on the participants window, or you can record your question in the chat window, or you can just unmute and go live. But I ask you to wait until the end of the talk. Okay, sorry, Anastasia.
No, sounds good. Thank you. Yeah, thank you for the introduction, Richard, and for everyone for having me today. I am coming to you from DuPont in Marlboro, Massachusetts. And today I'll be talking about some new enabling materials that we're working on for a couple of different emerging sensor technologies. So today we'll be focusing mainly on sensors and dipping into a couple of different technical examples in the sensor space. So let's make sure I've got the right thing. Yeah, so just to start off, I'd like to acknowledge some of the folks who are involved in the projects I'll be talking about today. Both my colleagues at DuPont and collaborators at Northwestern University in the HRSM and DIGTEL groups. So just a little bit more about my background so you kind of know who you're talking to today. I'm from the Port of Los Angeles, San Pedro, California. I started my academic career at Harvey Mudd College studying chemistry. And it was there I really realized that I liked a lot of different applications of chemistry. And so all of my different research directions led me to materials as my PhD topic, where I studied polymer physics and polymer chemistry, both in the very fundamental side of self-assembly and X-ray scattering, as well as the more applied side, doing marine anti-fouling coatings. And so it's that interest I had with, combining chemistry into physical properties that led me to DuPont's Emerging Technology Group in 2019. And so we are in the electronics and industrial business. And the project that I've been working on mostly since joining is looking at optical films with tuned refractive indices. And that'll be one of the projects that I'm covering today. So some of my goals for today are to introduce how new materials will enable emerging sensor technologies, so sensing capabilities that don't yet exist, and to tell you a little bit about the role that material designers have in the space. How does this ecosystem work, and where does a company like DuPont sit? And then I'll go into detail. The majority of my sort of 30 minutes will be going into detail on these two examples of gas sensing and optical sensing. And so I plan to come at this from sort of a systems perspective. So I'll bring in a lot of those design rules that we as materials designers think about. But given the audience, I thought it'd be great to kind of take a step back and look at it from a systems sort of overview. How do these get actually integrated into the device? And what do we have to consider for those types of processing steps on top of just those material properties? So for sensing in general, there's a lot of different arenas that sensing is growing in. A few of them are listed here. A couple that I'll point out for today's relevance are environmental sensing. So we'll be talking today about gas sensors. And so what comes to mind with gas sensing could be pollution and toxicity, really measuring our impact on the environment as well as health impacts. So that's one arena where gas sensing is becoming more important. And then in a lot of these applications, optical sensing is important, image sensing, basically cameras. Then one that stands out to me at least is this automotive example of, we have self-driving cars are an emerging technology, and so there's a lot of optical sensing opportunities there. So in terms of the ecosystem, this is sort of how we see our place in enabling some of these new capabilities. There are device designers who really well understand the performance targets needed for these different types of technology. They are experts, of course, in the fabrication processes. And so when I say device designers, I mean the companies and groups that are actually making these components and integrating them into the final devices. They also understand the manufacturing timelines that are needed if new materials need to be integrated. And we, as materials designers, we bring our expertise in chemical design and material properties. And our ideal arrangement here is that we're actually in contact with those component designers, those device designers, so we can understand the fabrication requirements and actually do some iterative testing such that whatever we develop is something that could actually enable the technology. It's not something that has some fatal flaw that we discovered later on. So it's the collaboration between the two of these groups that really enables new sensing capabilities. So that is sort of it for the overview. Now I'll be diving into, oh, I hear a little echo. Diving into two examples, gas sensing and optical sensing. And so I'll start with the gas sensors. I may deviate a little bit from Richard's plan and partway through this invite questions on the gas sensor portion of my presentation because we're going to be covering a pretty wide range of topics here with gas sensing and optical sensing. So before we move on to optical sensing, I'll pause for any questions on the first portion. And of course, I'll be happy to take any questions at the end as well. So I think everyone in the audience has one of these sitting on their desk or in their pocket. Our smartphones have a ton of different sensors in them, including physical sensors like accelerometers. but also, they can see. We have cameras, multiple cameras now on our smartphones. They can hear through microphones. And our question today is, can we make them smell? So an electronic nose, or e-nose, is often what's called, it's kind of the keyword right these days for gas sensing. So incorporating, on-the-go live read type gas sensing in mobile phones, but also other applications is really desirable. So to motivate gas sensing, it's really an emerging safety priority. This can be applied in the home environment, in industrial environments. And, there's ways to sense gases right now that are very sensitive, but don't really apply to these sort of on-the-job environments. And there's a lot of different contamination sources, emission sources, but really at the end of the day, it comes down to being able to measure low concentrations of very particular analytes or different, particular gases of interest. And so this is where, the gas sensing opportunities come in for more mobile type gas sensing. And just to orient everyone, the concentrations I'm talking about will be sort of in the ppm level is what we're talking about here. So for this particular project, our material design strategy was surrounding the motivating problem of food spoilage. So as food spoils, it releases different types of amine compounds. That's the main type of compound that is diagnostic of food spoilage. And this is really important because in the US, 30 to 40% of our food that's produced never makes it into anybody's stomach. It is wasted throughout the supply chain and in the consumer's hands, often due to spoilage. So the motivation for this project was, can we detect amines at relevant levels and concentrations such that, you can maybe have a red flag go off somewhere in the supply chain to prevent this food spoilage. So from a material standpoint, what we're talking about is sort of like that enzyme lock and key picture, where we have some sort of substrate that we've designed that is designed chemically to interact with our analyte of interest. In this case, it's an amine. So we'd like to match our analyte to our material functionality. Now, there's a number of ways to make devices that can do this. We'll be focusing on acoustic resonance sensing. And there's a cartoon I've drawn here that kind of describes how this works. So if we have some sort of material, which is kind of the gray box, with different absorptive sites, so we can design the chemistry of those blue sites. We can tune in the absorption and desorption of the gas into the substrate. And assuming that our substrate is a rigid oscillator, which is a good assumption for these devices, the mass difference as the gas absorbs and sticks to the substrate, that mass difference is going to correlate directly to the difference in the frequency of the oscillation of the substrate. So that's the signal we're getting. We're analyzing, we're basically counting up mass of the gas that interacts with the substrate, and the signal we're getting out is due to a frequency change in the oscillation. So in terms of material properties, the sensitivity, how low concentration we can sense is really dictated by the strength of those absorptive and desorptive interactions between the analyte and the film. The selectivity, which has to do with being able to recognize a particular gas in a host of other gases in a mixed environment, that's dictated by the specificity of the chemistry that we choose. So how specific can we make the chemistry on the surface to interacting with the particular analyte of interest? And the response time, to make it relevant for actual everyday use, is controllable by adjusting that film surface area. So you can imagine that the more absorptive type sites you have, the more quickly you can equilibrate with the environment. So in the actual devices, there's microelectronic approaches, which I'm sure this audience is much more expert on than I am, but there are definitely approaches to make these devices at really small scale. But in the lab, what we do is work with quartz crystal microbalances. So these are oscillatory substrates where we can actually measure that frequency difference that I was referring to on the left. So this is the kind of data that I'll be showing on the following slides. We have on the y-axis the frequency of that oscillation. So the bare substrate has a higher frequency, and as that mass absorbs to the substrate, the frequency slows, and you get this shift in frequency based on the difference in mass of the oscillator. And so, in the green box, we're adding mass to the oscillator, and then it equilibrates at some lower frequency. But then if we flush the system with some sort of clean gas like nitrogen, then we'll have desorption of those species, and we'll recover the original frequency from the bare substrate. So in order to make a material that can do all these things, we look back to this bottom left box, which I think I should get a laser pointer here. So we can look back down to this bottom left box and see what our requirements are. We are required to have sensitivity, selectivity, so we need to be able to tune their chemistry, and we'd like to have high surface area in order to have a relatively fast response time. So the material of choice here is going to be covalent organic frameworks, or CoFs. So these are molecular crystals. They're made up of building blocks of small molecules, and in the synthesis, they self-assemble into these extended, very highly controlled sort of geometric arrays that are crystals, basically, made up of these molecules. So there's a number of reasons why we like these for gas sensing. One is that the pore size can be engineered. So by changing the size of these linking groups, you can change the size of this opening, where the size of the opening is sort of order of magnitude 25 angstroms, just to give you a length scale. You can also design the pore shape by changing the connectivity of these different nodes. And there's a variety of linkage chemistries. This is a really proven chemistry. It's been studied for a long time. And so there's a lot of options in terms of what chemistries we can choose to interact with different gases of interest. And this is where we can get our selectivity. So in general, there's a lot of modular components here, a lot of really well understood systems. So it's a really nice material for pursuing in terms of gas sensing. And again, we'd like to be able to measure amines for our project here of interest. And so the rest of the materials I'll show on the following slides will have this, the boronic ester that is involved with the boron, basically the boron atom. It can attract the amines and have an intermolecular interaction there. And that's where we're going to get the selectivity for amines. So the only challenge with covalent well, there are many challenges with lots of materials, but a big challenge in terms of getting these materials into devices is their processability. So if we take these two starting materials, we have our boron here for amine selectivity. These react into the extended crystals. And in a conventional synthesis, they immediately precipitate and are, really hard to work with in terms of getting into a device. So one of the tricks you can play is a judicious choice of solvent. So by choosing solvents that interact more strongly with the components involved, you can actually get these stabilized suspensions or colloids of the covalent organic frameworks in solution. And so instead of this big mess that precipitates out, we can keep clear solutions that show, in this case, a laser pointer going through as a demonstration. Okay, so now we have all of our components. We have our covalent organic framework with the boron atoms for attracting the amine. We can make it into a stable suspension using a particular solvent combination. And then I'll be showing you some data from a variety of different material pore sizes to change that pore size, but all with the same chemistry. Now, how we actually make these devices is through spray coating. So because we can make this stable suspension, we can load up a spray coater with this colloidal ink and coat, basically any substrate of interest. And we can use masking to block off certain areas if we'd like to prevent those from being coated. So here's a microscope image of some masked areas showing where the colloidal ink is not being sprayed. And then here's our quartz crystal microbalance substrate for the actual testing. All right, so the first set of data I'll be showing you is based off of this material, CoF-5. It is the smallest linker and sort of the simplest to start with. So CoF-5 was dosed with a number of different analytes. So spray coated, created a film, and then dosed with all the analytes that you see listed on the right side of the slide. And on the left side, you see that frequency, or delta frequency versus time curve that I was cartooning earlier. So in most of the cases, as the gas is added to the system, there's some equilibration period, and then about 75 seconds into that, there's a leveling off of the frequency change. So this is all the mass that's going to be added, and everything's in equilibration at this point. And you can see already that there's, there's kind of a wide range of responses to different gases based on this particular material. There is higher sensitivity for amines like triethylamine, so that's a good sign for being able to use these materials potentially for amine sensing. But you may notice that one of these curves is not really like the others. Cadaverine here has a very strong response and a very slow equilibration time compared to the others. So there's a number of chemical reasons for that, but there's also a geometric reason, which is another reason why these materials are so cool. So if we do DFT simulations to look at the actual interlayer structure of these assembled materials, you can see that cadaverine actually fits exactly in this spot between these two boron groups. And so there's a strong interaction at this end and at this end. And so that combination of strong chemical interaction, as well as having it being bidentate by having 2 points of contact, it really highlights how both the geometry and the chemical functionality can be tuned to match, some target analyte. In this case, if you really wanted to sense cadaverine, this would be a great material. But we'd also like to sense other types of amines. So on the right here, I'm comparing the signal response for triethylamine and cadaverine in these 2 bars. So the material I just showed you on the left here, CoF-5, had that sort of weaker response to triethylamine and a very strong response to cadaverine. So on this next slide, I'll be showing you information on this far right material because we're interested in sensing triethylamine. Cadaverine is a molecule of interest applications, but triethylamine is another analyte that we're interested in looking at. So let's pick the one with the highest response to triethylamine to do some further studies. So we took that material, which I have cartooned up in the corner here, and dosed in different known amounts of triethylamine to basically build a calibration curve. So by putting in, 10 parts per billion, 50, 100, up to 1,000 parts per billion, and then measuring this frequency offset from the initial frequency, we can build this calibration plot that converts that frequency change to an actual concentration. And so one point I'd like to make for this particular material is it has very high sensitivity. I mentioned earlier that parts per million is sort of where we want to be for a lot of gas sensing applications. And here we're getting down to 10 parts per billion. So this was a great demonstration of how sensitive these materials can be. And then finally, for the gas sensing portion, we also demonstrated recoverable performance. So this is important if you want your sensor to be multiple use. If you want to be able to add your triethylamine into the system, have it absorbed to the surface, and then maybe you remove your spoiled fish, put in some fresh fish into your fridge. You want to be able to have that recovery back to the original sensor state so that you can measure the next sample. So this was cycled a few different times by cleaning out the environment and then re-adding in the analyte, and you do see the recovery each time to the initial state. So that's the first half of what I'll be talking about today, covalent organic frameworks as gas sensing materials. They're very good materials for gas sensing because they have those tunable chemistries and geometries both, which we saw was really important for sensing in particular cadaverine in this example. They've been made processable, which is really important for actually getting into devices. They're sensitive down to the relevant concentrations or even a bit lower, and they have recoverable sensing performance. So I can pause here if there's any burning questions on this first portion, and then I can introduce the next example.
Okay, we have one question that's loaded in the chat room. How does the sensor clean itself? Does it require periodic cleaning, maintenance, calibration?
Yeah, that's a great question. So this recoverable response that I showed here is just ambient conditions and just removing the source of that, of that analyte. So changing it out for clean air, and then just it equilibrates on its own at ambient conditions to desorb the triethylamine back into the atmosphere. There are approaches, though, for incorporating other components into the gas sensor. Let's say the material needs to be heated to recover its performance. There's ways to incorporate, small heaters into your device and things like that. But the ideal, of course, is in this case where just ambiently the desorption happens just as in the calibration process.
Okay, and I'm curious about what's involved in integrating this kind of sensor into a system where it might be used.
Yeah, so in terms of the application or the physical application, spray coating and those types of coating processes are definitely doable. Something I'll note about actually integrating them into real devices is that I can go back to this slide. Oh, it's trying to load. There it goes. Is that one consideration for these materials is that there's always going to be a little bit of response from other gases. We're not getting just 100% selectivity for any one gas in this material. So a lot of these gas sensors are going to end up being multiple materials in an array altogether. And it's their combined sensing and principal component analysis and software analysis of their responses that actually forms the final whole sensor.
Mm-hmm. So in typical use, you might need multiple sensors.
Right. So in typical use, a single sensor might have multiple materials in it. That's likely how it would end up being packaged up.
Hmm.
Richard, I tried to post a question, but I guess I didn't do it very well. I was wondering what effort is there to make an interface between the result of these the substrates that are collecting these data and an output that would allow some action.
Do you mean at like the device level or a little bit more metaphorically?
Well, perhaps at the device level, but you create a device. You create a device on a substrate that does this analysis, and then how does that device interface with a signal, a trigger to create an action?
Right. Yeah. So these devices will need some sort of processing involved. So the micro oscillators, not the quartz crystal microbalance that we use, but the actual devices micro oscillators will have that frequency output. And so there needs to be some processing capability, nearby to actually take that frequency output and apply the calibration curves that are known for that material. And as I was mentioning, take all the outputs from each of the materials in the sensor and deconvolute. Oh, if this one has a small signal and this one has a strong signal, then we know that it's more likely that this material's analyte is present, and that can account for different interferences between the two. So there is some brain power that's needed for actually interpreting the signal, since those interference effects can happen, and you need to be able to interpret frequency and convert it to the actual concentration.
So most of it is probably an analog sort of output rather than just a binary output.
Yeah, I believe so.
Okay, we have another question in the chat space. Does the sensor have temperature or humidity limitations?
Also another great question. Yeah. So covalent organic frameworks, these particular materials are very stable if you're thinking about temperature. So that's something, if you're going to have a sensor to monitor air quality in a vehicle and it sits in a hot parking lot, then that's definitely a consideration to keep in mind, is what types of environments will these be exposed to? Or even if you have a sensor, in the powertrain of an actual engine, then that's something else to consider.
Mm-hmm.
These particular materials are very stable to pretty intermediate temperatures. And at ambient temperatures, they last, at least 18 months with no degradation. So that is something, though, in general for gas sensing to keep in mind, since many of these materials, can be kind of sensitive.
Yeah.
For the,
I would
oh, go
I would
ahead. Sorry.
imagine the adsorption must be temperature sensitive.
Yes, yeah, that equilibration, there's a rate constant there, and so there's a temperature dependence, definitely. And that's another, to Harvey's question, another sort of process that needs to be taken into account for the interpretation of the data.
Hmm.
And then I think humidity was the second part of that question.
Yeah.
Humidity is always a challenge for gas sensing because many of these materials will have some sort of response to water vapor. And so that's, again, where that principal component analysis comes in, where you have a material that's very sensitive, let's say, to humidity, and is much more selective to water. So if all your other sensors are giving a signal, but it's really just mostly water in the air, you can do that analysis between the different sort of crosstalks of the sensors.
So that sounds to me a lot like the interface has to be multi-channel, not only what the rate is or what the volume is, but what the conditions are at the same time to give it a perspective. Is that right?
Yes, yeah, exactly. So there are very good humidity sensors that are very good at just measuring water. And so that would be a channel that, you can take with a little bit more certainty and feed that into, into one of those channels and have temperature maybe also. And then, with those more certain inputs, you can interpret the other inputs.
Excellent. Thank you.
Okay. So if we don't have any more questions about this section, maybe we can proceed to the second.
Sounds good. Yeah, so the second example I'll be going over is optical sensing. So kind of a 180, at least in the sensor world, from gas sensing. And in this portion, I'll be getting a little bit more into the actual process integration. So we'll get a little bit more into like film mechanics and polymer physics of that. So again, kind of a 180 in material systems here. So in image sensing, image sensors that we're all familiar with are the cameras on our phones. That is an image sensor. And so our analyte now is light or photons. And the signal, instead of a frequency change from our oscillator, is now just the electrons coming from, let's say, like a photodiode or some other sensing material. And so the places you might see advances in image sensors showing up is in places like autonomous driving, like I've already mentioned. A lot of really cool things in medical imaging. And then, another example is augmented and virtual reality headsets are bringing in a lot of camera tracking. So again, when we need these new functions, this is what really inspires new materials. So the new functions in image sensing are miniaturizing the components. I think all of these sensors have the drive to miniaturize. In images, that means densifying the data because the area of your sensor directly correlates to the number of pixels and the density of data that you collect. Another new function, which I'm not going to get into today, is expanding the wavelength sensitivity. So actually changing the sensing material to leave the visible spectrum into the UV or the IR. But then the last function I've listed here is one that we'll actually talk a lot more about today, which is getting to higher sensitivities. And this translates to maybe like a low light situation or a time where there's fewer photons coming in, but you still want to be able to accurately count them. And so again, when we push the limits of the current materials, that's when we come in with new enabling materials if we can. So again, I mentioned kind of miniaturization, high resolution, and sensitivity. Those are all really actually related concepts. So if you look at this plot from Yole development, looking at the advances in the image sensing arena here, we have pixel size on the y-axis, and we're looking at basically micron-sized pixels at this point, and then resolution across the x-axis at the bottom here. So in all of these areas that image sensors are used, they're really aiming towards often these sort of low pixel sizes and high resolution. And if you zoom in on what the image sensor is actually doing, this is, a kind of a blow up of a mobile phone camera. The image sensor itself is in the back here, but there's a lot of different layers on top of it. So these optical layers are also really important in terms of collecting light. And the more we shrink the pixel size down this plot, the same number of photons are hitting the material, but with smaller and smaller pixels. So each of those buckets is holding fewer photons than it used to if it had been a bigger bucket. And so because of that, very small, percentage changes in the efficiency of light collection can make a really big difference in the sensitivity. And these optical layers are really what dictate how much light gets to the back of the camera. And you can see, there's lots of lenses that happen that are placed way out here, but then in the back of the device, there's a lot of optical layers involved. And what dictates light collection versus light reflection, which is not what we want to have in terms of collecting photons, really is the refractive index of those films. And so that's what I'll be focusing on for the second portion, is controlling refractive index of these types of optical films to increase the efficiency of collection based on these reflection type interactions. But also, the higher refractive index you have, the thinner your material. So I have a pretty strong prescription of my glasses. I always get the higher refractive index lenses so I can thin down and have less material. So that's another benefit to controlling refractive index. And so this is important, for directing light to some endpoint, either in the light collection space, like I was just describing with cameras. But if you imagine a display, it's just a camera in reverse in terms of those interleaving layers, where you're trying to direct light with high efficiency. So just as a reminder of how refractive index at interfaces work, if you go from a high refractive index medium and try to get light into a low refractive index medium, there's often reflection at this interface, and it depends on that difference in refractive index across the interface. So for example, if you've ever been swimming and you've gone underwater and looked up at the surface of the water, you see a lot of reflection, and that's because of that refractive index difference. If you have the opposite situation, then you don't get reflection, but you do get refraction. And so going in from a low refractive index medium like air into a high refractive index medium like this camera lens, we can get refraction, and this is really the tool of choice for directing light through different pathways and devices. So we'll be, really trying to tune in the difference in refractive index between materials, and the example I'll be showing you today is based mostly on trying to get higher refractive index materials. So, okay, I've been saying the word refractive index a lot. How do we actually tune refractive index in terms of material design and chemistry? So here's a relationship that relates refractive index n to a number of different variables, two of which I've highlighted here as really the main physical properties that we can control: the density of the material and the polarizability. And both of these together directly relate to increasing the refractive index if you increase them. So density kind of makes sense intuitively. If you have a very frustrated packing or a lot of void space in your material, you're basically averaging in a lot of air or vacuum into the pathway of light. And that's going to reduce the refractive index towards something like air with very low density. So if, for example, if we use the covalent organic frameworks from the gas sensor project in an optical film, it'd probably be very, very low refractive index because there's so much void space in those materials. And of course, the opposite is true. If you have very close packing or high density, then you get high refractive index. And that's something you can imagine sort of like a diamond. That's very high refractive index. Polarizability is a little bit less intuitive, but if you think about this in terms of, sort of like the chemical idea of electron clouds. So if a material has very polarizable electrons, if the electron clouds are sort of big and fluffy and easy to push around by radiation, then that contributes more to refractive index. So for example, if you move up the halides from fluorine all the way up to iodine, you can see that that contribution to polarizability increases just because the atom is getting bigger, the electron cloud is getting less tightly held. And so that contributes to refractive index. So for some examples, PMMA acrylics are the sheets of plastic you see between you and the cashier these days. Its refractive index is around 1.5 in the visible spectrum. But if we replace this sort of very dipolar group into an aromatic group, then we can get a higher refractive index because those aromatic electrons are all very polarizable, very delocalized. And so that increases the refractive index to around 1.6. And if we go to the extreme and start replacing different atoms with larger atoms like sulfur, that boosts the refractive index even more to around 1.8, which is very high for organic materials. So we have these two tools. We have density and polarizability. For organic materials, density is not as easy to change. So we'll be mostly talking about high polarizability functional groups. So as I mentioned, everything we do is in contact with a customer who has performance metrics that are relevant for actually, for getting new devices realized. So I just mentioned, some performance metrics we need to keep in mind are, of course, the refractive index target, which we have polarizability and density handles for that. But in choosing those functional groups, we have to keep in mind that they can't be absorbing in the visible spectrum. If we used this very highly sulfur-containing molecule for our film, this actually has a red color, and so all of your photos would look like they had a red filter on them if we put that in the path of light. So we already have something that kind of, could be in opposition here, colorlessness and refractive index in terms of the chemistry choice. We also need to keep in mind, taking a step out in length scale on the microstructural scale, is that these films need to be optically clear. So they can't have any aggregation or haze creating elements in them that scatter light. And so this might bring to mind some sort of composite approaches that are often taken for increasing refractive index, but can create these kind of aggregation effects that are bad for the efficiency. And then taking one more step out to the rheology and the mechanics scale, anything we do, any choices we make on this side have to be compatible with fabrication processes on the right side. So this could mean some sort of target viscosity, a solvent choice, a curing process, even shelf life. So the theme of this portion of the talk is going to be that a lot of our desired properties have trade-offs with other requirements that we need to keep in mind. So getting into the actual experiments and steps that we ran, the first challenge we ran into was a solubility issue. So again, we're targeting high refractive index materials here. And because these groups by design are very polarizable, they have very delocalized electron clouds, it means that they don't really have those dipoles in them that help them become soluble in the organic solvents that we'd like to use for coating. And so that's already sort of an inherent opposition in the material design. So what we can do is dose in just a little bit of solubilizing groups, which tend to be low refractive index, but we can get away with incorporating a very low amount, just enough to solubilize the material. So that was one of the first lessons we learned in this project. Another challenge is that a lot of these materials that tend to be high refractive index also tend to have poor mechanical properties. So we were working with our customer and looking at our different materials, and they noticed in their fabrication process there was a lot of cracking on the wafer. And so that's something that obviously is not very good for an optical sensor to have cracks throughout it. And so our first thought was, okay, this is a polymer-based system with a crosslinker. Let's just add more crosslinker. Let's increase the fracture toughness of the film by just making a denser cross-linked network. So, if you kind of zoom in on the cartoon version, we had some amount of crosslinker that we had optimized for in the beginning, but in order to prevent the cracking, we increased the crosslinker. We added more of that small molecule. But of course, that molecule tends to be low refractive index, and so the more we add in, the more we're going to dilute the optical properties that we want to keep. Something else to keep in mind is the integration of this component eventually in the film or in the device needs to undergo different thermal stresses. So here I've shown percent transmittance versus wavelength. So this is a UV vis spectrum. And we like to keep our percent transmittance at 100% basically across the visible. But this film is coated, and then that part of the device gets integrated into the whole device. and it undergoes different thermal stresses. The greatest of which you can think of is the solder reflow step. So our film needs to be able to endure the solder reflow temperature around 260 C for a certain number of minutes. And so if we go from the black curve, the original film, and do some thermal stress tests, you can see the effect, the translation of this data is basically a yellowed film. And again, we don't want color in the films. So already just on this one slide, we had solubility issues to consider, similarly film mechanics to consider, and a lot of it has to do with balancing in small amounts of the components that we need to fix those problems without pushing it too far in the other direction. And so the second challenge we mostly fixed by including much more crosslinker in the film and making a stronger network. But we noticed in collaboration with our customer that no matter how much crosslinker we added, there was still cracking, and it really shouldn't be there based on the amount of crosslinker we added. So there was something else going on. So we took a step back and looked at the actual coating process and asked, that's the question, where does this actually happen in the film, in the film creation process? So this is a spin-coated material. It's dispensed on a silicon wafer. It's spun to set the film thickness, and the edges are rinsed off with this edge bead removal solvent. It's then soft baked to remove much of the solvent and then cured. In this case, it's with heat, but it could be with a lot of different stimuli, like light. So again, we're thinking about cracking. We're thinking about what's actually happening physically with these polymer chains. In this, when it's first dispensed, they're very solvated and mobile. And then at the soft bake step, a lot of the solvent's driven off. And so we get viscosity building and much less polymer chain mobility. And then after the chemical cure, that's when the structure is locked in. That's when the crosslinker activates. And so we had assumed that this very extreme step was when that cracking was developing in the film, because it's the highest temperature change. It's the greatest chance for stress to be induced in the film. But when we asked, when does the cracking actually occur? Can we pull the wafer each of these steps and take a look? We wanted to consider all these different physical properties and states of the material at each of these stages. And we learned that the cracking actually starts at the soft bake step, so not where we expected. And it really highlighted that need for us as material designers to be in touch with the actual process, so we can make the right changes to fix the problems. So we asked all these questions. What is the actual, what is the properties of the material at each of these stages, and which of these types of measurables can we look at in order to solve the cracking issue? So we took a look at this soft bake step. And again, when we look at this film, before we even get to the cure process, there are cracks. So I've kind of indicated a little bit the regions where cracking exists. I hope you guys can see that. But there's long cracks that cross the film in this direction as well as in this direction. And again, what we're looking at is the left part of this microscope image is the actual polymer film, and the right portion is where that film has been rinsed off at the edge of the wafer. So we're already getting cracking at the soft bake step, and this is due to that reduced chain mobility. A lot of the solvent has been evaporated, so there's enough reduction in the chain mobility that we can't actually relax the stress that's being induced. We can measure the film stress at the soft bake and cured steps. And so you can see that the stress does increase quite a bit in the cured film, but there is significant stress in the soft bake film. So this bar is what we're going to be trying to target and lower. So a lot of times, if you're thinking about polymer physics and glass transitions and things like that, plasticizers come to mind. If you're trying to reduce stress and let the film relax, you can add a plasticizing element. But you might guess that I'm going to say that plasticizers tend to be lower refractive index. And so that was not a great option for us in terms of something that would stay in the film. So instead, we took the approach of adding a volatile plasticizer, so something with low molecular weight that could evaporate at the end of the whole process. So, adding a little bit of volatile plasticizer into the system allows the chains to relax and suppresses that glass transition. So now our image is crack-free. So now our film has none of those cracks that we saw in the previous state. and the film stress that we are trying to lower is greatly reduced in the soft bake. And you can see that the film stress is maintained after the cure to the same number. So, this film stress, as well as a lot of other indicators, tell us that the plasticizer completely leaves the film in the cure process. So we get back the material that we wanted in the first place while fixing this intermediate problem on the way. So that was, 3 challenges that we met with high refractive index materials. We, designed in on the chemical side, high polarizability functional groups. And, those brought up a number of challenges in terms of the film properties and the solubility. And so working with our customer, we were able to fix those by really diving into the process. So in conclusion, thanks everyone for listening. I was talking today about how new materials will enable these new emerging sensing technologies, and how, in order to deliver them this kind of performance and make these realized in the real life, it really requires collaboration between those device makers and material innovators, so we can bring those lessons of chemical design, material properties, and very importantly, the fabrication process into the same space. So thanks everyone for your attention. I'd be happy to take any questions about the image sensor or the whole talk.
Thank you, Anastasia. Interesting pair of talks, actually. I have one question to pass along from the chat room. Does curing in vacuum make a difference?
Oh, that's an interesting question that brings up a few points. Curing in vacuum for this material would not make a difference, as the cracking kind of started earlier on. But curing in vacuum would be important to avoid some things like discoloration. So a lot of, I will go back actually to the previous slide, or 2 slides ago. What I showed in the bottom corner here, this discoloration occurs likely, often due to oxidative mechanisms. So if you had a great chemistry, you really wanted to use it, and you could convince your device maker to use a vacuum cure to prevent this kind of discoloration, then that would be a way that the vacuum would actually become really important.
I see. And I have a question of my own. Are there, I believe the general theme here is that you're looking for workable high index materials, because everything could be made smaller, thinner, more effective. And obviously anything you can do with organic chemistry makes things easier than doing it with inorganic. But what I was wondering was, are there competing non-polymer approaches to high refractive index, and how would those approaches compare?
Yeah, that's a great question. Yeah, you definitely notice that we're really focusing in this talk and in this project on more of those organic materials. One approach that's often taken is through sort of a nanoparticle approach. So, maybe having some sort of polymer binder that's suspending some sort of metal inorganic type nanoparticles. And that's something that can really increase the refractive index. You can see composites like that going up to 1.8, 1.9 refractive index. But it really depends on the application and the environment that material is going to end up in. So, for example, some customers prefer not to have those types of composite materials because of the haze type aggregation that can develop over time. So, especially in industries like automotive, where it needs to be extremely reliable over long periods of time, then there's less of a desire to use those composite approaches.
See, Harvey, you want to give your questions? I see you have a couple.
Okay, I guess I'm not muted. I was just wondering if the rate of curing and perhaps even curing under pressure might have changed the rate of fracture creation that you demonstrated.
Yeah, those are both interesting variables. for rate, the rate of cure can definitely make a difference because you can partially cure like 10%, let's say, of your crosslinker, and then give your material a chance to relax as it's curing the rest of it.
Exactly.
Yeah, so that is an interesting approach. It again depends on sort of what is possible in the fabricator's hands. So that can be sort of tool limited. Something else though that can be really important is not so much the rate of cure, but the rate of cooling, because it's
Right.
often the cooling from the cure step that, that's what is, you have some sort of expansion, in your material when it's hot, and then it's going to shrink at a different rate than the substrate. That kind of mismatch is what creates the tensile stress in the film.
Right.
So cooling slower. Oh, go ahead. Yeah.
Yeah, I assume you get some differential shrinking between even the individual molecules as the temperature drops. But you want to get your curing done uniformly, I would assume.
Right.
Across,
Yeah.
across the whole structure, even though it's very thin.
Yeah. That also actually goes back to Richard's question, maybe, or what I kind of answered to Richard's question with the composite approaches. Those can actually, exacerbate the problem of that thermal expansion mismatch,
Right.
because you have very different materials, in the same film.
Exactly.
But even in this case, it's, the interface between this more organic film and the silicon wafer, or whatever substrate ends up being, in the actual device. That mismatch also is what is driving the tensile stress in these particular materials.
Sure.
So that's always going to be there. And yeah, the rate at which you cool, especially from those elevated temperatures, can really give some time for the chains to relax, because they'll be more mobile at higher temperatures. And then if you give them that kind of relaxation time through to the lower temperatures, they have a better chance of not cracking.
Okay. Alejo, would you like to speak up, or shall I read this?
Yeah, I can speak up. By the way, Anastasia, amazing talks. Like Richard
thanks,
said, two talks,
Alejo.
and I mean the back and forth between just molecular design and material and application and kind of like fitting into the device. That's the whole mile. It's really cool. So quick question. I know you were comparing these to camera lenses, and I guess one thing I was wondering is, can one create a gradient of compositions or a gradient of cross-linking degrees across the film to recreate the effect of a curved lens, but on a flat film?
That's a really cool idea. Yeah, that is possible. And it's one of those sort of a little bit right now, a little more out there kind of approaches. The thing to keep in mind with gradients is basically the length scale that you're creating that gradient on really matters. So, a lot of these films are kind of like on the micron, tens of microns kind of scale. So if you could create a gradient on those length scales, then that would be really neat. But some of these films are so thin that you're actually approaching, the wavelength of light. And so at that point, if you have a gradient at the top of a 500 nanometer film to the bottom, you're getting into sort of different effects there, because your material properties are changing on the order of the wavelength of light. But in sort of these thicker films, I think that's a really cool way to really smoothly go from one refractive index to another, definitely.
Right, and could you do it on a kind of like lateral gradient from center to edge?
Oh yeah, center to edge, that would be, I think in terms of a functional sense, that'd be a lot easier to do, definitely. I know that in terms of lens creation, there's a lot of advances in thinning things out, like Fresnel lenses, and changing the properties of the material based on its thickness. And so if you had, the center kind of, I think you're kind of imagining, like if we had a 3D plot of refractive index over area, you could kind of make that lens shape, but sort of print it into the material.
Right.
And that would be really neat.
Cool. Well,
but
amazing talk.
But Alejo, I don't think she can do it on a bouncing ball.
I don't know. After this talk, I'm convinced that she could do a lot more things. Anyways, thank you so much. That's such a good talk.
Thank you. Yeah, thanks for your question. That's a really cool idea.
Okay, so let's thank our speaker one more time.
Thanks, everyone.
Thank
And
you so much.
Thank you very much. Yes.
And I have one final slide to put up before everybody takes off. So there we go. So this, as the slide indicates, this is our third virtual technical meeting. They seems to be a pretty good format. Let's see, we need to go to the next slide for the next. Oh, well, actually, the schedule for the next virtual technical meetings are to be determined, but they will be brought to your attention with emails and on the chapter website. So thank you for our speaker, all the participants, and just a shout out for the next IMAPS New England Symposium virtual session. The next one is Advanced Packaging, and it will occur on April 15th. And it will be followed in June or July, exact date to be determined. Will that be the final one, Dave?
Well, we seem to be continuing. We don't know yet. We're getting
Okay.
down to the end. We're exhausting our list of sessions that we had prepared for the 2020 symposium. So
yeah, but seeing as how the
close to
symposium,
the end.
the annual symposium has now kind of spread out over more than a year, I think we're onto a different beast. So at any
True.
rate, keep an eye out for as the schedule gets firmed up for this last one. And thank you all for participating.
Thank you, Richard.
Thanks, Richard. Thanks, Anastasia.
Have a good night.
Thanks,
Not
everyone.
all.
Thank you.
Hey, Anastasia, are you still
I'm here.
listening
Yeah.
there? Did you ever put up an email or a contact?
Oh, I forgot to put that on my slide, but I'm happy to share it. Yeah.
All right, maybe
So-
yeah, if you want to just dictate or put it in the chat, but that'd be great.
Yeah, it's pretty easy. It's my first name dot last name at DuPont.com.
DuPont.com. Okay,
Mhm.
that's easy. All right, I may shoot you an email about a couple of questions. I
Yeah,
actually
please do.
I work directly on gas sensors, so I have
Awesome. Yeah.
some interest. Okay.
Very cool. Happy
All
to
right.
talk more.
Anyway, it was a great talk. Thanks. I appreciate it.
Thank you.
I can't even see my face here. Sorry.
Thanks.
Well, I'll shoot you an email.
Sounds great.
Okay. Thanks.
Bye.
Bye.
Okay, I'm going to turn off recording now.
Okay.
And